Welcome back to the Learning Daily Physics. And we have discussed about the Bohr atomic model, and today we are going to talk about, we are proceeding our lecture, and we are going to talk about the effect of nuclear motion on the Bohr theory. So we were discussing about the Bohr atomic model, and in Bohr atomic model we have said that the nucleus is at rest and electron is revolving around the nucleus. So earlier in the previous lecture we said that we have this nucleus here, and around this nucleus we have an orbit, and around in this orbit the electron is revolving here with this velocity v. So we were assuming first that this nucleus here is at rest, but now today in today's case we said that the effect of nuclear motion here, nuclear motion, this time the nucleus is also revolving around an axis of rotation. Let's say that about its center of mass, about the center of mass of this nucleus or this electron, both they have a common center, and at that common center nucleus is also revolving, and this common center we said that this is the axis of rotation of this nucleus. So what happens, previously we have seen that when this nucleus is at rest and simply this electron is revolving around this nucleus, so we have seen our results that what happened to the result when this nucleus is at rest. But this time now we are going to talk about that when this nucleus is also in motion, then what happened to the Bohr's theory. Then what happens to the Bohr's theory when this nucleus is also moving and this electron is also in a motion. So now we will talk about the relative motion, and when we talk about the relative motion in the 2-point system, in the classical mechanics we have seen that when 2 point masses are relatively in motion, then we collectively take their reduced mass. And today we are going to talk about the reduced mass, and we will see that how reduced mass is used here when we consider the motion of the nucleus and this electron. So now you have understand what we are going to do and what we have to do and what is the main goal of this lecture. So let's proceed our calculation. So for our calculation we have to make a more general diagram. So starting with this, that we have a nucleus N like this, and we have an electron E here. This is an electron. Now this is the displacement R from this nucleus, from the center of this nucleus to the center of this electron. Okay, so this is the displacement R. Let's make a line passing from the center of this N and this E, nucleus and electron. Now they both have a common center. Let's say the center of mass. So as we know that the mass of this nucleus is much heavier than the mass of this electron. When the mass of this nucleus is much heavier than the mass of electron, so when we talk about the center of mass is more shifted toward the heavier one. For example, we say that we have a seesaw, what we call that, a seesaw like this. Okay, so the center of mass will be shifted more where we have more mass. Okay, so our center of mass for this will be shifted from here to here. Okay, so now same as in this case, as our nucleus is more heavier than this electron, so our center of mass will be shifted more toward this, and we call that this is a CM, common center. this is the common center, and from here to here we have negative of x. I will tell you why this is negative of x, because we are taking this as a reference point and this is left to the reference point, so we will say that this point is negative of x. So, and this, what will be this displacement? This displacement will be this displacement minus this displacement. This negative sign is just because of the reference point, it is left to the reference point, so it will be r minus this displacement, which is x, whose magnitude is x. So this will be r minus x. So now you understand the diagram, I think. So let's move on toward the theory now. So in the theory we are going to write that let the nucleus and the electron, let the nucleus, from this diagram we are going to write that let the nucleus and the electron revolving around a common center. Okay, so this nucleus and this electron is revolving around this common center. So we said this, which is C of m. So common center have coordinates x, m and y, m. So we say that this center of mass is only shifted along x or y axis. There is no movement along, or there is no change in the coordinates along y axis. It is at origin with respect to y axis. So we will say that first this y of m will be equal to 0. Okay, so now for the center of mass, starting from equation of center of mass, so xcm is equals to x1 m1 plus x2 m2 divided by total mass, which is m1 plus m2. So according to our case, we are going to write the mass of this nucleus is equals to capital M and the mass of this electron is equals to small m. Okay, so putting these values here in this equation of center of mass, so we will have xcm equals to x1 is equals to this minus of x, and we are going to write this minus x, m1 is equals to capital M plus or minus x into small m divided by capital M plus small m. Okay, so now what we are going to do, we are going to say that as this y of m was at 0, this xcm is also at origin. Okay, this xcm is also lying at origin and this xcm is also equal to 0. When this xcm is also equal to 0, what we are going to do, we are going to put this xcm equals to 0 and it will be 0 equals to minus x capital M plus or minus x small m divided by m plus m. Okay, so this will be our equation. This term here multiplies here and equals to 0. Okay, so now this minus x m plus r minus x m equals to 0. Okay, so you can see here. Now what we are going to do, we are going to multiply this and separate this x. So let's see that minus x m plus r m minus x small m. This one is the capital M and this one is small m. So now what we are going to do, we are going to take minus x common from this term, so it will be minus x into m plus small m plus r m equals to 0. this term is in minus, it will go that side and it will become a positive term. So I'm going to erase this side. So if you haven't write this, so you better write it first. Okay, so now it will be equals to that R of m will be equals to x into m plus m. Okay, so from this x will be equals to R, this one is the small m divided by capital M plus small m. This is the one value we have find out, which we are going to use in our equation. And further, when we are going to calculate this equation is, we are going to use this equation. I am writing this equation as equation number 8. So now what we are going to do is, we are going to say that R minus x will be equals to, I am going to put the value of this x here. So it will be R minus x will be equal to R minus this R m over m plus m. Okay, so then I'm going to take the LCM. So it will be R m plus R capital M minus R m divided by m plus m. So this term will get cancelled out, and the term what we will have, R minus x will be equals to R capital M over m plus m. Okay, so I hope you can see these two equations we have find out. So now I'm going to write these two equations here above, that we are going to use this equation number A and B. So now we have find out that how we found these equations. So I'm going to write these equations here above. So x equals to R small m divided by total mass m plus m, and similarly R minus x equals to R capital M divided by total mass m plus m. So these are the two equations we have find out. So now why we found out these equations, now let's talk about that, why we are finding out these equations. So we are finding out these equations to put in the, we are going to calculate the total angular momentum, because in Bohr theory, when we talked about the Bohr in the first lecture, when we talked about the postulates of this Bohr, so we said that the angular momentum is conserved and L is equals to mvr. L equals to mvr equals to nh cut. Okay, now we are going to talk about that when this nucleus moves and this electron moves, whether this satisfies or not. Okay, so this is the term what we are going to do, and we have to find out the total angular momentum, which will be the component part of the angular momentum of this nucleus and the angular momentum of this electron. So to find out these, when we are going to find out these values, we have to put these two values of these from these equations. So we have find out this value of this x and R minus x first to find out this total angular momentum. So I'm going to erase all of this. I hope you wrote everything. I'm going to change my duster first. It makes my whole board more dirty. Let's carry on with this. So now we are going to talk about the angular momentum. So as I told you that the angular momentum L will be equals to N plus LE. This is the angular momentum of this nucleus, and this is the angular momentum of this electron, and this is the total angular momentum. So now what we are going to do is, we know that I n omega plus I e omega. Okay, this is the angular frequency and this is the moment of inertia. So moment of inertia of the nucleus and the moment of inertia of electron, and this is the angular frequency. We know that the L is equals to I omega, which is equals to the mr square. I is equals to mr square, and this will be equals to, because for this it is equals to x square m, as I is equals to mr square. So for this it is x square minus x square, or magnitude, we are talking about the magnitude. So it will be m, mass of this nucleus, and then x square mr square and into omega. Okay, so this is the angular term for the nucleus. Okay, so now for electron, similarly for the electron, the mass, which is m, and this is r minus x whole square into omega. So I hope you can understand that how these equations are formed. We simply put the value of this in this equation. So now what we are going to do is, we are going to put the value of this x and r minus x we have found out here. That's why we find these values to put these values in this equation. So from these two equations, putting these two values here, you can name that, as we named it, equation number A and equation number B. So we can say that from equation number A, and B, from equation number A and B. So putting these values here, it will be m omega into r m, x is with the small m, and you have to take care about that. So plus small m into r m plus m, and we have a square here and a square here and an omega term. Okay, so this is our equation which we have made. So now what we are going to do, we are going to take common things common, and it will be m omega r m square over m plus m square plus m omega into r capital M square over m plus m square. Okay, so now we are going to take the common things and we are going to solve this equation, and by solving this equation, what we will have, first, if you don't have write this, you have to pause the video and you have to write this. So write every equation as I'm writing, so write every step with me, that you can understand more better. So now solving this equation, taking common, so it will be, L will be equal to, you can see now, yes, so m small m r square, when you are going to take the common, it will be a term like this, and here the common term will be m plus m whole square. So you have to take this m is also here, and it's an easy step. I'm not going to take your time for that. So this square will be cancelled out with this one, you can see, and the term we have is equals to r square omega into m m over m plus m and this term. So this term here is equals to mu. This term here is equals to mu, and it is r square omega into mu. L is equals to r square omega mu. So this is our equation, and what this mu is, let's see. So you have write down this. So I'm going to erase this first. So what this mu is, let's talk about that, what this mu is. So this mu is equals to reduced mass. This mu is equals to the reduced mass, and I told you earlier that in the beginning of this lecture that when we take the relative motion of 2 point masses or two masses, then we talk about their center of mass and we consider their reduced mass. And this L is equals to now r square omega mu. We know that V is equals to r omega, and omega is equals to V over r. So putting this value of omega here, so we can see that r square V over r mu, this r will be cancelled out with this one, so this will be equals to mu V r. So L, this is the L, angular momentum, when this nucleus is in motion, is revolving around the axis of rotation. This is the axis of rotation, and this electron is also revolving around this axis of rotation. So now what is the difference? Now we are going to calculate what is the difference between when this nucleus is at rest and when this is not at rest. Okay, so in the next lecture we will discuss the results, that what happens to the radius when this motion radius is greater than with the reduced mass or not greater with the reduced mass. So in the next lecture we will talk about that. But in this lecture, let's see that what is the difference between Bohr theory without reduced mass and with reduced mass, or Bohr theory with nucleus at rest or with nucleus in the motion. So in the first postulate, we said that L equals to m v r. So when we compare this equation with this one, you can see in this equation and in this equation, let's say x and y equation. So look carefully in equation number x and equation number y. You can see that this v, this L is same as this one, this v is same as this v, this r is same as this r. So where the difference is between this mu and this m. Okay, when this electron was the only one who was revolving around the nucleus, okay, then the mass was the only one mass of this electron we were considering. When this nucleus and this electron, they both are moving, then what happens? Then we talk about the reduced mass. And in the next lecture we are going to talk about that, how this reduced mass affects the Bohr's theory, affects the results of this Bohr's theory, that what happens to the r prime, what happens to the wavelength, what happens to the Rydberg constant, what happens to the velocity. So this is everything what we are going to calculate in our next lecture. So till then, assalamu alaikum.